3, 2. Hello and welcome, class, to another lecture here in Chapter 14, where we are discussing reaction kinetics. Now, I'm not going to spend a lot of time prefacing what we're talking about today because we will be focusing on the dependence of our reaction rates on the concentration of our reactants and products. So there's a lot to talk about today. Let's just start getting right into it. All right, so let's start by discussing how do we even measure reaction rates? How do we study the kinetics or the speed with which our reactions progress? Well, we're going to start with I just said that, so 3, 2. The average reaction rate is measured by a change in concentration over a period of time. So literally all we're observing with what is known as the average reaction rate is how the concentration is either decreasing for a reactant or increasing for a product as time progresses. For example, and we're going to be focusing on this example for like the first half of today's lecture, let's say we are observing the reaction of 2 nitrogen monoxides with a single oxygen gas molecule, and this turns into 2 nitrogen dioxides. Well, in this graph, what we have represented here is the measure of the concentration for each of our molecular species, where nitrogen monoxide we can see is represented by the blue line, oxygen gas is the orange line, and nitrogen dioxide is the grayish kind of black line. And we can see that both of the reactants, the nitrogen monoxide in blue, the oxygen in orange, are decreasing in concentration as time here on the x-axis progresses. So over the course of this reaction, it looks like we're going from 0 seconds to 8,000 seconds, where again, the second is the metric or standard unit of time. The product in our gray, our nitrogen dioxide, we can see starts at 0 because there's none of it present initially, and as the reaction progresses, our concentration here is increasing. All right, so how do we then find the rate of the reaction? It seems like we have 3 different things here that we can focus on, right? We have either of the 2 reactants, or we have the product. So what do we focus on to calculate our change in concentration over the period of time that has passed? First, we're going to introduce the rate of formation because, as it turns out, you can pay attention to whatever you want to pay attention to inside of your reaction as it progresses. So if we start with the perspective of the product, the calculation of our rate of formation is going to be dependent on the formation of the product. Now, in the reaction that we are hypothetically observing here, paying attention to and measuring the concentration of nitrogen dioxide as it's forming is actually a pretty easy thing to pay attention to, because nitrogen dioxide, as we can see pictured here on the right, is this orangish brown, very obviously present gas, even in low concentrations. Conversely, nitrogen monoxide and oxygen gas are both clear, colorless gases. You can't see them, you can't really smell them. Nitrogen dioxide has a very clear odor and it is very visible. So it's going to be pretty easy for us to pay attention as the concentration of our nitrogen dioxide increases. We're going to see an increase in the saturation of this color. So the way that we measure the rate of formation is by taking the final concentration of our product, and that's what these little brackets here represent. We're going to be seeing this notation a lot from here on out throughout the semester. A bracket notation with something inside represents concentration of whatever is inside. So here I have brackets around X. This would mean concentration of X. That should be a quote. Give me a second. All right, 3, 2. All right, there we go. Put my quotes in to make sure that I am properly open and end quoting here. So we're going to take our final concentration and we're going to subtract out the initial concentration. Now, the final minus initial doesn't necessarily have to be the very end of the reaction versus the very beginning. It could be between any 2 selected time points. What matters is that we are also then going to be dividing this change in concentration by a change in the corresponding time. Whatever the final point of time is minus the initial point in time, the important thing here is that we are measuring a change in the concentration of our NO2, our product, divided by a change in time. All right, so let's go back to our previous graph and let's pick out two different time points for our nitrogen dioxide just to calculate a rate of formation. So let's pick out, it seems like we have some really nice intercepts if our time points are 2,000 and 3,000 seconds. So if we follow up, we can see that there is a starting concentration at 2,000 seconds of 0.04 molar NO2. And after an additional 1,000 seconds has passed, our concentration has increased to 0.05 molar. So this means our rate of formation, which is equal to the change in the concentration of our NO2 divided by the change in time, is going to be equal to 0.005 molar minus 0.004 molar. And as I said, we don't have to pick the very beginning and the very end of the reaction. So long as we're looking at data points here, a corresponding X and Y, all we really need is two data points that could be anywhere. So our quote-unquote final, in this case, is going to be at 3,000 seconds. And we're going to subtract out the quote-unquote initial at 2,000 seconds. All right, so if we take the change in our Y divided by the change in our X, in other words, the change in our concentration of NO2 divided by change in T, we find a rate of our reaction equal to approximately 1 times 10 to the negative 6 molar per second. All right, so this is the rate at which the reaction is progressing forward from the perspective of our product. Now, of course, we can see that there are a couple of other curves here present, right? We have the nitrogen monoxide as well as the oxygen gas. So let's say hypothetically, if we wanted the rate of reaction to be measured from the perspective of that reactant, how would we go about it? Well, instead of a rate of formation, we would instead be paying attention to a rate of consumption. This is the rate dependent on the consumption of our reactant, the rate at which the reactant is consumed by the reaction and disappears. So if we're again paying attention to the exact same reaction, no longer paying attention to our product, instead just picking out, let's say, one of our reactants, the nitrogen monoxide, the rate of consumption is going to be equal to a negative because here our reactant is being consumed. We are literally losing reactant. As we lose reactant, we need to make sure that this rate is represented with a negative sign here. We'll be taking the constant or the final concentration of the reactant, again at some time point, and subtracting out the initial concentration of the reactant at an earlier time point. So again, final minus initial, ending minus beginning. It doesn't necessarily have to be the very end and the very beginning, just so long as we're looking at two different data points. And so we can more concisely state the rate of consumption for the nitrogen monoxide is going to be a negative delta concentration of NO, or the negative change in the concentration of the nitrogen monoxide, all divided by a change in time. All right, so again, let's go back to our previous graph. And I'm just going to clean this up a little bit. All right. All right, 3, 2. All right, so we are going to pick out the same time points because we want to keep a little bit of control here. Not only for the sake of control, but also it's a little bit easier to see where the data points are intersecting on the y-axis here. So it looks like initially at 2,000 seconds, our nitrogen monoxide had a concentration of 0.006, and 1,000 seconds later, we have a concentration of 0.005 molar. All right, 3, 2. So we are going to insert these concentrations into our rate of consumption equation for our NO2, which is a negative change in concentration of NO, not NO2, NO, our reactant, divided by a change in T for time. So a negative final concentration, which is 0.005 molar, and we're going to subtract out the initial concentration here, our 0.006 molar. Take this all divided by, again, 3,000 minus 2,000, which is a difference of 1,000. So I'm kind of cheating a little bit here. The difference in our... No, I'm not going to do that. I'm not going to skip. Don't skip steps. All right, 3, 2. So we're going to take this difference in concentration and divide it by the difference in our time. So again, the final time is our 3,000 seconds, and we're going to subtract out the 2,000 seconds that we started with. And the change, or the rate of consumption for our nitrogen monoxide, let's see, I'm going to write up here just because I didn't leave myself much space, is also 1.0 times 10 to the negative 6 molar. So the rate at which nitrogen dioxide is being formed is actually the same rate at which the nitrogen monoxide is being consumed. Now we can kind of see that visually on the graph as well, because really what we're measuring here is, again, a change in y divided by a change in x. We're looking at a rise over run. In other words, we're looking at a calculation, an average of the slope represented here. And obviously I didn't draw the straightest lines in the world, but the slope of the rate of formation is the same slope as the rate of consumption. The only difference is that one is negative, but because the rate of consumption equation has a negative sign here numerically, the rates end up being the same. Well, this is great for the nitrogen dioxide, our product, as well as the nitrogen monoxide, one of our reactants, but we can see that the oxygen gas with this orange curve here does not follow the same pattern as the nitrogen monoxide. So we can ask ourselves the reason, or we can ask ourselves the question, what is the reason that oxygen does not follow the same rate of consumption as the other reactant? Well, to answer that question, we need not look any further than the balanced chemical equation. We can see that the nitrogen monoxide, one of our reactants, and the nitrogen dioxide, our product, have the same stoichiometric value in front of our molecules. This means that the rate with which one of these is being used up is going to equal the rate at which the other is produced, because they're being used and generated proportionally by the same factor. Oxygen here has half of the stoichiometric coefficient, which means it's going to be used up at half the rate. We won't need as much oxygen for every cycle through this reaction. And so we can represent this by observing quantitatively that the stoichiometry of the chemical reaction is going to also provide us with a relative measure of our rate. In other words, relatively, 3, 2, twice the number of moles in a chemical reaction will take half as much time to react. Now this is going to follow the exact same observation that we made on the graph previously. If we have a 2 in front of the nitrogen monoxide, that means that we have to use 2 times more than the oxygen. Therefore, it gets used up twice as fast. So if we want to make sure that our chemical rates, our reaction rates, are going to be equivalent to each other, if we want to recalibrate them, let's say, so that way the rate is all going to be the same, how we do so is by taking the stoichiometric coefficients in front of a species in our chemical reaction and dropping it into the denominator of a fraction, and we can set all of our rates equal to each other in this way. So, for example, half of the rate of consumption for our nitrogen monoxide should be equal to the rate of consumption for our oxygen. Similarly, half of the rate of formation for our nitrogen dioxide should be equal to the rate of consumption for the oxygen. Now we can state this theoretically. We can also go back to our graph and calculate this quantitatively just to provide even further support for these equations and for this argument. You know, so let's do just that. All right, 3, 2. All right, so we are going to pick out the exact same time points. Again, we want to keep everything in complete control here. So between 2,000 and 3,000 seconds, we're going to observe where the y-intercepts are for the rate of consumption in our oxygen. Where are the, what's the starting concentration? We can see here, as well as the ending concentration, which would be exactly halfway between 0.008 and 0.007. So we're going to take these concentrations and insert them into a rate of consumption equation for our oxygen. So we're going to be observing the negative change in concentration of oxygen divided by a change in time, inserting the values that we just picked out from the graph. So a negative starting concentration of 0.0075 approximately molar minus the 0.008 molar. And again, we're taking it divided by the same time points, the final time being 3,000 seconds, and we're going to subtract out 2,000 seconds. So concentration per time is going to give us the rate of consumption for our oxygen, which here when we crunch the numbers, we end up finding 5 times 10 to the negative 7 molar per second. In other words, we are looking at 0.5 times 10 to the negative 6 molar per second, which is exactly half of the rate of formation of the nitrogen dioxide and half of the rate of consumption for the nitrogen monoxide. So we can attribute this exactly to our stoichiometric coefficients out in front of our species. Because there is only a 1 in front of our oxygen, it gets used up half as quickly, and therefore its rate of consumption is half as much as that of our other reactant, the nitrogen monoxide. All right, 3, 2. All right, so if we turn our attention back to the relative rates and stoichiometry slide here, what the takeaway message is from this slide, from this observation at how the rates of the consumption and the formation kind of, work together, is that if we only have the time to pay attention, let's say to the rate of formation of one of our products, assuming that we can actually calculate the rate of formation right here, using the balanced chemical equation, we can relate the rate of formation, formation, to any of the other rates of formation, as well as the rates of consumption for the other reactants here, where the rate of formation is specifically the value that's inside, aside from the fraction out in front. Similarly, our rate of consumption for oxygen is in the square outline here, and the rate of consumption for the nitrogen monoxide is going to be here. We can just relate them to one another using the stoichiometric values. All right, 3, 2. All right, so far we have seemingly not discussed much, but maybe it does feel like it's been a lot. We, again, in summary, have been looking at reaction rates as measured through concentration changes over time. So here in this example slide, we are told that the rate of NO2 formation in the previous reaction is 0.124 molar per second. And I would like you guys to find what is the rate of consumption of our oxygen. And 3, 2. And so you don't have to go back to any of the previous slides or scrub backwards in the video. Our balanced chemical equation, again, is 2 nitrogen monoxides plus an O2 gas goes to 2 nitrogen dioxides. 3, 2. Wait. All right, 3, 2. All right, so we just learned how we can use our balanced chemical equation to determine the rates of our other species, assuming that we know the rate of at least one of them. And in this case, we have a rate of formation. So our nitrogen dioxide is being created. Its change in concentration per change in time at this particular moment in the chemical reaction is 0.124 molar per second. Now we know that this rate So we know that 1/2 of this rate, 1/2 in the change of our NO2 divided by change in time, is equal to the change or the negative change of the concentration of our oxygen per unit of time. Okay, 3, 2. So we can see here, all we need to do is insert this 0.124 into this portion of our equation, literally finding 1/2 of the rate of formation, 0.124 molar per second. And this is going to give us the rate of consumption for our O2, a negative in parentheses. While it's going, I'm just gonna take a drink while the dumpster truck's doing its thing. All right. Blah. 3, 2. What? Yeah, I'm just gonna say. I'm just gonna go back. I don't remember where I was. Oh no. All right, 3, 2. So if we insert our rate of formation into our equation right here, what this tells us is that the rate of consumption for our oxygen is equal to 1/2 0.124 molar per second, which is equal to 0.062 molar per second. And this is what our rate of consumption is going to be equal to. Now, I know this might appear a little strange to have a negative symbol in front of our change in oxygen, but then no negative sign down here in the actual rate. But remember, a couple of slides ago, as we were calculating these rates of formations, the rate always ends up being positive because in our rate of consumption equation, the change in the concentration of our reactant is going to be a negative value, right? So since the final concentration is lesser than what we started with, the change is going to be a negative number. Negative times a negative ends up being a positive rate. All right, so let's just take a little bit of a breather before moving forward. In, again, conclusion thus far, we have seen that chemical reactions can have measured objective rates as we observe what the change in concentration of either a reactant or a product is over some change in time. So we're graphically also looking at the equivalent of the slope of the line, the slope of the curve as concentrations change over time. So moving forward, it's going to be really useful for us to really start thinking about these changes in concentrations over time as the, 3, 2, as the tangent of the curve, as the tangent to the curve of concentration versus time. And so as we observe the tangents, really what we're doing here is measuring what is known as an instantaneous rate. This is the rate at some specific instant in time as opposed to changes of time. So we're no longer looking at average rates, we're looking at instantaneous rates as time progresses. Now we can see that this instantaneous rate is going to change as a function of time since this curve sort of flattens out as time progresses. So we have a really steep curve here, a steep slope here, since the curve is really like pointing more sharply upwards. The slope begins to flatten out at time B and then really begins to the slope is becoming equal to 0 here as we get to point C. So for this reason, when it comes to measuring instantaneous rates or reaction rates in general, it's best to observe what we call the initial rate. This is specifically the instantaneous rate at the very beginning of the reaction as soon as the activation energy has been overcome. And the reason why this particular rate, this initial instantaneous rate, is the one that we observe the most is because it is also going to be the most consistent to observe. It can be a little bit tricky to try and observe reaction rates after certain points of time as the reaction has been progressing, just because as the reaction progresses, there are certain environmental factors that can actually lead to differences in how fast the reaction is progressing forward. Subtle changes in temperature, subtle changes in how quickly the reaction was stirred or what type of energy was put in to overcome the activation energy. These can lead to slightly different shapes of the curve as time progresses. However, this instantaneous rate at the very beginning, as soon as the reaction starts, is going to be consistently the fastest rate and will also be the most consistent as a result. Three, two. All right, so we're going to keep this in the back of our mind. The instantaneous rate at the beginning of the reaction, our initial rate, is going to be the rate that we're going to be observing and working with for the rest of lecture today. Three. Okay, 3, 2. Now, what we're going to be working with, how we're going to be using these initial rates, can be described as using them in conjunction with rate law expressions. You see, chemical reactions are not just dependent on the rate of consumption of one independent reactant, but the reactants coming together. And so rate law expressions are a way for us to observe how the rate is dependent not just on one of our reactants at a time, but all of our reactants at the same time. So the initial concentrations and rates can be used to determine this reaction's, what is known as its rate law expression. The expression representing symbolically, right, through language, the equation used to calculate the rate. A rate law is the equation that relates the rate of the reaction specifically to the concentration of all of our reactants, plural, where the dependence of the rate on a particular reactant is proportional to what it's known as its reaction order. So that is a mouthful. Let's use the example of the generic equation down below to better understand what this rate law expression is, what the rate law equation is. So let's say we have hypothetical reaction of reactants A plus B turning into products C plus D. And we can see that these little lower cases out in front here, the lowercase a, b, c, and d, are going to represent the stoichiometric coefficients in front of the reactants capital A and capital B, as well as the products capital C and capital D. This form of a generic equation we're going to be seeing a lot for the rest of the semester, so I just want to explain what this notation means now. All right, so we would predict then in terms of the rate law expression that the rate of the reaction as it progresses is going to be equal to what is known as the rate constant, and is represented by this lowercase k, times the concentration of A, and specifically, since we're going to be focusing on initial rates, we also need to observe that this concentration of A is going to be the initial concentration of A. And we're going to take this initial concentration of A and raise it to the rate order M. So this M is going to depend not only on the identity of the reactant, but specifically what reaction we are working with. In other words, this reaction order, this exponent on the reactant A, is going to not be constant. It's going to be like 1 or 2 or 3. It could be any integer, all depending on what specific reaction we're working with. So we're going to talk about how we can find these reaction orders for our particular reaction in a moment. All right, we're going to take concentration of A and multiply it by the initial, again, since we're working with initial rates here, concentration of reactant B. And reactant B, we can see also is raised to a particular exponent. This is going to be the reaction order of B. Now the exponents M and N could be equal to the same thing, but they don't necessarily have to be equal to the same thing. A particular reaction could be more dependent, specifically the rate of the reaction, could be more dependent on one of our reactants than another. And so we're going to represent how the rate depends on these concentrations via the reaction order, via what these particular exponents are equal to. Now, if we turn our attention back to this rate constant K, we're going to put, I'm just acknowledging now, we're going to put a pin in what this rate constant breaks down into, but for now, I will say this rate constant is where the like temperature component of the reaction is, like the temperature dependence. It's where the activation energy dependence of our reaction is. So there are a lot of variables that go into what the rate constant K is equal to, and we'll be talking about that in more detail in part 3 of the kinetics lecture. So for now, we're just going to say the rate constant, lowercase k, is a constant, and we're not going to worry yet about what variables it's dependent on. All right, so our rate law So our rate law expression is a more comprehensive means for measuring the rate of our reaction because, again, this calculation incorporates both of the reactants or all of the reactants at once. So we're not looking at an independent rate of consumption, we're looking at the overall reaction rate as it's dependent on both of the reactants turning into products. 3, 2. All right, so what we're gonna spend a fair amount of time doing is working through this example problem here, and we're gonna do it together because unless you were in like AP chemistry in high school or had a more advanced course and saw this type of problem already, it can be pretty intimidating and very, let's say, I'm gonna use the word tedious, but I don't necessarily mean it in a bad way. It's just very detail oriented. So what we do to find the more comprehensive rate law expression is through observing a series of data points, our initial concentrations versus initial rates. So let's say nitrogen monoxide is reacted with oxygen gas, we're using the same previous equation that we've been working with, in 3 different trials. And the following initial rates in this table, the initial rate of our nitrogen monoxide, as well as, the initial concentration, nope. 3, 2. And the following initial reaction rates we can see in the table down here are found. Our question is, what is the overall rate law expression that we can use to represent the speed of this reaction? So again, we're looking more generically than just the consumption of one of our independent reactants. Here we are looking at the overall rate of the reaction through both of the reactants simultaneously, like together as these 2 things are reacting. What we need to find to more comprehensively solve for this rate law expression is K, M, and N. Once we have our rate law constant as well as our rate orders, M and N, these exponents, we can use this rate law expression to calculate the rate for any amount of starting material. Any initial concentration of NO and O2, we would be able to predict how fast the reaction would be out of the gate using this rate law expression. Well, before being able to use this equation, we need to figure out what these missing constants are, the K, the M, and the N. So how we're going to do that is by cleverly observing 3, 2, our data down below. Now, throughout these trials, we can observe between trials 1 and 2, it looks like the concentration of nitrogen monoxide was held constant. It was held in control. In other words, we are observing how altering the concentration of oxygen initially impacted the initial rate. Similarly, between trials 1 and 3, it looks like the concentration of O2 was held constant, which means trials 1 and 3 will be useful for determining how the concentration of the nitrogen monoxide impacted the rate. 3, 2. So the first step in solving this type of problem is to select 2 trials where one of our reactants is held constant, so we can observe more explicitly how the other reactant is going to impact the rate. All right, 3, 2. All right, so I'm going to flip between this slide and a blank slide in order to actually show my work and how to approach this problem. So to start, we are going to pick out trials 1 and 2 and compare the data between trials 1 and 2 to determine what the rate or what one of the rate orders of our species is. Specifically, we are going to be observing the rate order N between trials 1 and 2 because our oxygen is the species that changes concentrations here. Right, so since the oxygen is changing concentrations between trials 1 and 2, this is going to be useful for finding our rate order N. How dependent are 3, 2, and again, our N represents how dependent is the rate on concentration of oxygen. All right, so let's flip to this blank slide. What we're going to do, or what I'm going to show you, is a systematic way to break down this type of problem and very easily be able to solve for our rate orders. How we do this is by comparing the proportion or comparing the ratio of our rate for trial 1 to our rate for trial 2. What's the proportion here? By how much did the rate increase or decrease between trials 1 and 2 as a function of changing our oxygen's concentration? Now, since we are working with the rate law expressions here, we know that the rate for trial 1 is equal to our rate constant times the concentration of our NO to the M times our concentration of O2 to the N. And again, this is for trial 1 concentration NO and trial 1 concentration O2. The same thing is can be said for our rate 2. Again, since we're looking at the proportion of rate 1 to rate 2, this is also like looking at the proportion of our concentrations initially, our nitrogen monoxide in trial 2, as well as our oxygen gas in trial 2. Three, two. So this type of setup of looking at the rate for one of the trials divided by the rate of another one of the trials is always going to be our initial like out of the gate kind of setup. This equation is going to be, or this like proportion, is going to be super useful to us, and it may not initially seem like it's going to be because there are so many variables here, but check this out. We're going to insert the rate for trial 1, which to go back to our data is the rate for trial 1 presented right here, this 1 times 10 to the negative 6, 1.0 times 10 to the negative 6, and we are going to divide it by the rate for our second trial, this 5.0 times 10 to the negative 7. 5.0 times 10 to the negative 7. Well, this is equal 3, 2. Well, this is, wait. Pen. Okay, 3, 2. Well, this is just equal to the number 2. We're literally taking 1.0, like one number. 3, 2. We're literally taking, like, right, 1.0 times 10 to the negative 6. This is twice as large as 5.0 times 10 to the negative 7. It's the equivalent of taking 1 divided by 1/2. We get the number 2. So it looks like between trials 1 and 2, the rate of our reaction halved itself. So 1 divided by half is equal to 2. We're going to see 3, 2. We can conclude that the rate of the reaction cut itself in half because of how we change the concentration of our oxygen. Since the rate constant K is a constant, and similarly the concentration of nitrogen monoxide in trial 1 between trial 2 was held constant, that should be an N, taking a constant K, dividing it by a constant K, cancels out, and taking the same concentration of our nitrogen monoxide raised to the M, just to go backwards to confirm, we're taking 0.010 and dividing it by 0.010. This gives us also a number of 1, and these two things cancel out. All that's left is the concentration of O2 in the second trial, which changed. right? In other words, the rate constant is the same between trials 1 and 2. The concentration of nitrogen monoxide remained the same between trials 1 and 2. The only thing that's different is the concentration of our oxygen. Now, this allows us to see or calculate specifically how the concentration of oxygen halved our reaction rate, again, giving us this value of 2. If we insert the concentrations from the table pertaining to trials 1 and 2 for our oxygen, which we can see right here, we're taking 0.01 and dividing it by 0.005. 0.010 raised to the n, all divided by 0.005. And again, we have an m for molar here. We're raising all of this to the n. Well, the way that algebra works out, how fortunate for us, is that we can take these exponents here in each of these separate, numerator and denominator, and pull them out. In other words, 0.01 raised to the n divided by 0.005 raised to the n is the same thing as 0.010 molar divided by 0.005 molar raised to the n. The molars here cancel out. And what we are left with is 2 to the n, right? Since 0.010 divided by 0.005 is just 2, it looks like the ratio of our rates is 2, and the ratio of our concentrations for oxygen between trials 1 and 2 was also 2. So our question is, what exponent must n be equal to? In other words, what exponent do we raise 2 to in order to get 2? N must be equal to 1. In other words, the rate of our reaction is directly proportional to the concentration of O2. If we go backwards here, and I'm going to clean this up a little bit, our N is equal to 1. If we double the concentration of O2, we would expect our rate to double. If we triple the concentration of O2, we would expect our rate to triple. These two terms are directly proportional to one another. And in fact, this is exactly what we just saw returning to the data. Between trials 1 and 2, we cut the concentration of oxygen in half, and we saw that the rate got cut in half. Mathematically, demonstrating this can be a little bit more tedious. As I said, the process, we want to be able to... 3, 2... The process is thorough, it is consistent, it's always going to get you to the right answer. This process, specifically right here, but it just looks a little bit complicated and it can be very easy to lose exactly what we're observing. What we just found is the proportion with which our rate depends on oxygen and its concentration specifically. Next, we're going to have to change our focus, turn our attention to the nitrogen monoxide to find what the rate order M is equal to. In other words, how does the concentration of the nitrogen monoxide impact the rate of the reaction? How we find this is, as I pointed out earlier, observe trials 1 and 3. Since between trials 1 and 3, our oxygen is being held constant. This is going to mean that we can use the exact same trick that we just saw when solving for N. If we're holding one of our reactants constant, in working through the math here, it's going to cancel out and allow us to more directly find the exponent we're trying to observe. All right, so give me a second to clean this up. And there we go. I want to keep our original equation, except now we're going to be comparing trials 1 and 3, so I'm going to change these subscripts of 2's to subscripts of 3's. There, that's good enough. So let's observe the proportion of the rate from trial 1 to the rate of trial 3. Well, the rate of trial 1, again, is that 1.0 times 10 to the negative 6, and we can see that the rate of trial 3 is 2.5 times 10 to the negative 7. So 1.0 times 10 to the negative 6 molars per second, all divided by 2.5 times 10 to the negative 7 molars per second. Now, the proportion of our reaction rate ends up being equal to the factor of 4. In other words, the rate in trial 1 is 4 times greater than the rate in trial 3. We can use this information to find what our rate order M is equal to by using, again, the same trick that we saw before. Rate constant, K, is going to be multiplied by the concentration of our nitrogen monoxide in trial 1, which we can see here is equal to 0.010 molar, all raised to the M. The concentration of our O2 is also a 0.010. Concentration, 0.010. We now know that N is equal to 1, so we can just leave a little 1 up here. We don't even really have to include an exponent of 1, since anything raised to the 1 is just itself, but I want to be explicitly clear here. We're going to be dividing all of this by K, and then of course the concentrations of our species in trial 3. The concentration in trial 3 for our nitrogen monoxide is 0.005 molar, and we can see the concentration of our oxygen again is held constant. 0.005 molar raised to the M times 0.010 molar raised to the 1. Well, what do you know? Our rate constant, which is a constant, is going to cancel out. And here we can explicitly see that the concentration of our oxygens here is going to cancel out, leaving us only with the proportion of the concentrations of our nitrogen monoxide, the 0.010 molar, raised to the M, all divided by the 0.005 molar raised to the M. All right, so we're going to use the same algebraic rule as what we did when finding N. We're going to take the exponent and raise it out of both the numerator and denominator, giving us 0.010 molar divided by 0.005 molar, all raised to the M, which is equal to 2 to the M. Right, since 0.010 divided by 0.005 is just 2. So now we can see that as the rate of our as the concentration of our nitrogen monoxide is doubled between trials 3 and 1, its rate increased by a factor of 4. In other words, the rate of trial 1 was 4 times faster because the concentration of NO was twice as large. So we can use this information to find our exponent M. In order for this equation to be true, M is going to have to equal 2. So we can insert now this into our rate law expression right up here. Our M is equal to 2. So this tells us how the rate is dependent on the concentration of nitrogen monoxide. If we double the concentration of nitrogen monoxide, the rate should go up by a factor of 4 because of this square. If we triple the concentration of our NO, what this means is that we're going to be taking 3 squared, the rate is going to increase by a factor of 9. If we quadruple the concentration of our NO, 4 squared is 16, meaning that the rate is going to increase by a factor of 16 times. So we can see that the rate of reaction is ultimately more dependent on the concentration of our nitrogen monoxide as opposed to the oxygen, where it's just a direct proportion. All right, so far so good. We have seen how we can use the concentrations, these initial concentrations here between a couple of different trials to find our initial rate of reaction. All that remains is finding our rate constant K. Now, finding rate constant K is arguably the easiest portion or the easiest part of filling in our rate law expression because we no longer need to observe multiple trials. Really, we just need to pick out one. And the reason why is now we have one equation, and so long as we pick out the information from one of our trials, we really or reasonably only have one unknown. Since we can fill in a rate and we can fill in these concentrations, the only unknown here is K. Three, two. All right, so what I'm going to do here on this new blank slide, this fresh space to work, is rewrite our newly minted rate law expression. Since we know what our rate orders are, our NO concentration is raised to the 2 and the O2 concentration is raised to the 1. We're just going to pick out the information from trial 1 on the previous slide and fill it in here to solve for K. The tricky part is not numerically solving for K, but rather solving for what its units are. Yes, our units are still going to be important here, and the rate constant K is going to have some crazy looking units. All right, so we're going to keep that in the back of our mind. Let's grab the rate as well as our concentrations from trial 1. So 1.0 times 10 to the negative 6 molar per second is equal to K times the concentration for our NO, which is 0.010 molar, to the 2, multiply this by 0.010 molar raised to the 1. All right, and here again, we can see explicitly that we have one equation and one unknown. So let's rearrange and solve for K. First, I'm going to keep everything on the right-hand side just to condense things down a little bit. So we are going to have 0.010 molar cubed. Since now we can, since our base is the same, we can add the exponents together. Again, a really nice algebraic rule for simplification. 3, 2. This is going to give us K times 1.0 times 10 to the negative 6 molar cubed. All right, so we can see then to rearrange and solve for K, all we need to do is divide each side by 1.0 times 10 to the negative 6. So 1.0 times 10 to the negative 6 molar per second divided by 1.0 times 10 to the negative 6 molars cubed gives us a value of K. Now numerically, in this case, we see something super special occur where K is actually equal to 1. Now, this is not always true. In fact, it's rarely true. Very special circumstance here that our K is numerically just equal to 1. But as I said, the tricky part is not necessarily the calculation of K, it's the units. So we can see that our units here are looking pretty crazy. 3, 2. So what we're going to do is condense everything down. We have a molarity unit divided by molarity cubed times second in the denominator, and this is going to simplify even further to 1.0, 1 divided by molarity squared second. Now again, these units are a little crazy looking, but the importance of these units will be getting more into... No, don't do that. 3, 2. But the importance of these units is that they relate our concentrations on the right-hand side of the equation with the rate as measured in molar per second on the left-hand side. So one kind of hand-wavy explanation is, well, the units are there to make sure that all of the rest of our units work out properly. But there's something even more 3, 2, powerful in the units. So let's make an observation here. We can see that the rate order of our nitrogen monoxide is 2, and the rate order on our oxygen was 1. And as we added these two things together, we got a value total of 3. Well, notice that the exponent in our molarity down here is a 2. The exponent on the molarity in your rate constant K is always going to be your overall rate order minus 1. So if you're ever working with let's say, a problem where you know your rate constant K, and this might pop up in the homework, this might pop up on a quiz or a lab. If you know these units, add 1 and you can find what your overall rate order is. This is going to be a super handy trick, not only to double check your work to make sure that you have the correct orders in the first place, but also it gives you a little bit of insight as you start working what types of answers you could be looking for. 3, 2, 3, 2. But in the end, what we have found thus far now is our rate expression for this equation. The overall rate expression is going to be equal to our initial rate equals 1.01 over molar squared seconds times the initial concentration of our NO squared times the concentration of our oxygen to the 1. So now the super usefulness of this equation is we can calculate exactly the rate at which our reaction would start, provided we know the initial concentration of our NO as well as the initial concentration of our oxygen. So the last thing we're going to do today is actually use our rate law expression to do just that. We're going to find the initial rate of the previous reaction, assuming an initial concentration of 1.2 molar NO is mixed with 2.3 molar oxygen gas. So since the equation is relatively straightforward to use, I want to give you guys the chance to process not only the equation, but the units, how everything plays together, and calculate this last initial rate for the day. 3, 2. All right, so we're coming back together. The rate of our reaction in this case, again, is equal to 1.0 1 over molar squared seconds times the concentration of NO squared times the concentration of O2 to the 1. So again, there is no one universal rate law expression. Each reaction will have its own, and we can use some measure of like initial experimental data, some initial trials like we saw previously, to fill in the gaps, to figure out our K, to figure out our M, to figure out our N. So once these things have been done, all we need to do is insert some set of initial conditions and initial concentration of our nitrogen monoxide, let's say hypothetically, equal to 1.2 molar, and we're going to square this. And then we're going to take the initial concentration of our oxygen gas, this 2.3 molar, and we're going to raise that to the 1. So it looks like we have 1.0, 1 over molarity squared times seconds, times 3, 2, 1.44 molarity squared times 2.3 molarity. So here, like again, numerically, it's pretty easy to work out. We're going to be taking 1.44 and multiplying it by 2.3. But before crunching those numbers, again, I want to pay real close attention to our units. As we take all of our units and combine them together, we're going to be taking the inverse of molarity squared and multiplying it by molarity squared. So as it turns out, these two molarities will cancel out, and we will only be left with molarity per second. So this also means that our rate, the calculation of our rate, is going to be consistent with how we know rates to be measured, concentration units per second. So at the end of the day, the rate of our reaction is going to be 3.31 molar per second. This reaction is going to be progressing very quickly, proportional to the initial concentrations that we are working with here. All right, 3, 2. So this type of problem, again, can be tedious, it can be tricky. There are a lot of numbers to pay attention to, and so I am going to heavily encourage you to get practice with this type of problem well before studying for the exam. not only focus on working through these problems as a part of the homework assignments, but go out of your way to find additional example problems, whether they be in the textbook or online. Find additional problems from the back of the chapter, or maybe something from Khan Academy or SciShow. Something to really sink your teeth into to get a lot of practice with this so you can see the patterns to solve this type of problem before last minute cramming, right? The more practice you get with this, the better it's going to stick in your long-term memory, and the quicker you will be able to solve this type of problem, the more efficiently you'll be able to solve it, and the more confident you'll be in your work. And so we talked about plenty of big new topics today. How we find concentration, how we measure it quantitatively, how we measure reaction progress, as well as how the reaction rate is going to depend on the concentration of your reactants. So here we have plenty of suggested problems. Again, practice, practice, practice. We're getting to the part of the semester where everything matters, every problem counts. So if you do have any questions, please do not hesitate to shout out in any way. Whether you're in my class directly and you send me an email or you drop a comment down below, please let me know if you have any need for clarification. If you have any homework, please double check and do your homework. And as always, until next time, class is dismissed.